चलो फोन करना पड़ेगा। लैटवा क्यों जलाया रसोई में बेटा? लैटवा को पूरी जगह बंद कर दे बेटा जी। सारे ऐसे करता है जी। क्या हो गया?
डाले
हाँ?
डाले जो पानी होता है
उतनी नहीं, हम बोतल में ले लिए पानी। छोटी बोतल में। इसमें गिर जाता है पानी ना।
तो उसका ढक्कन किधर है?
ढक्कन होते हैं।
ठीक है ना।
ढक्कन कैसे फेंक दे? सब बोतल में एक जगह बांध के रख दी है। बाप रे। सब्जी कौची है ये?
मिर्ची
आय?
मिर्ची
ले ला मिर्ची।
और मिर्ची और मिर्ची वाली आचर को बोलना था वो बोल देगा मिर्ची
अब ये भी है।
मेरा नेट धीरे चल रहा है कंप्लेन करने आएगा अभी पता नहीं कोई वायर टूट गया इसमें वायर खींच दिया लगता वहाँ से इसमें वायर खींच दिया है कपड़ा सुखा देगा वायर के ऊपर
ना दिमाग खराब है
इसने खींच दिया था वायर वहाँ से खंबे खंबे से कनेक्शन है कि कहीं कहाँ से कनेक्शन होता है इंटरनल इशू बना रहा है
कपड़े तो भाई मैं सुखाई कितना दिन से नहीं धोई बेटा कपड़े तो धोई नहीं सुखाऊंगी कपड़े कपड़े तो सारी में डाल के रखते हैं
About internet connectivity diagnostics of geofiber service. Introducing geofiber diagnostics.
नहीं लिए हैं कि इनके दिमाग में घुस गया सुबह सुबह हम बोलती है रे नहीं लिए खाली अंडा लेके आके अगर तुम नहीं बोली तो मैं क्यों बोल रहे सुबह लिए नहीं खाली अंडा लेके ही है
See if
This conference will now be recorded.
okay. Yes. Good morning, everyone. Whether it's audible online.
Yes, sir.
Yes.
Yes. Mm. Yes. Thank you, everyone. Okay. Today here we are to discuss on PD demo. I will just give you the overview that what we will do in the advanced part of PD. Right? And I hope for everyone the PD basics is done. Right? I need not to tell what is PD. Right? What we do in PD. PD basics. In brief, we have discussed everything. Right? Input files, everything we have discussed. So today I'll tell you how the advanced part works and what we will discuss in advanced part. What are the topics done and what design we are using. So all those things we will discuss in the today's session. Right? So just give me 2 minutes. Yes. So now, what do you think the role of PD engineers? Can you tell me PD demo? What is role of
Like,
PD engineers?
like we have the gate level netlist, and now we want to make the layout, physical layout.
Yes, very good, right? Correct. See, ultimately, what is the role of entire VLSI engineers is to fabricate IC. Main intention is to what? Fabricate IC. What is IC? Integrated circuit. So where is IC is fabricated? Yes, good, right? IC is fabricated in
On
foundry. The foundry is a place where IC is fabricated. So when this IC is fabricated in foundry, right? What foundry understands? Either foundry understand the Verilog code, foundry understand VHDL code. No, the foundry will understand only the layout. Foundry will understand only GDS. GDS file is required for foundry to fabricate IC. Foundry to fabricate IC. GDS2 file is required. So what is full form of GDS? Graphical data stream. This file is required to fabricate an IC. What GDS2 consists of? GDS2, what it consists of? GDS2 consists of layout, layout of cells and its connections. Right? That is what the GDS2 consists of. So ultimately, what we are found is we are the GDS of the site. And this GDS is not generated hardware, generated in the software. The software is called as what? EDA tools. So we use EDA tools to generate We use EDA tools. EDA tool means what? Electronic design automation tools. We use electronic design automation tools to generate this what? GDS with efficiency. Tools are used to generate GDS of IC, which works with efficiency. Efficiency means what? The IC should have what? IC should have less power, less area,
Area.
should have less area, and it should be having no functionality failures. No, should be working with high operating frequency, should be having high operating frequency. IC should be ready to work with what? High operating frequency. No manufacturing failures. See, manufacturing failures may happen during IC fabrication, but we have to ensure that it should not happen. So there are some rules which you have to follow. So no manufacturing defects. Testing facility after IC is tested, right? We have to see that IC can be easily tested, right? Testing facility. So all these things we should ensure in an IC. To ensure this, what we do is we use what? Electronic design automation tools. Yes, sir. So what is ASIC design flow? So to ensure all these things, this IC will not never fail in all these aspects. We use what? ASIC design flow. So the ASIC design flow, right? When I talk about ASIC design flow, first step we start with what? Specification. Specification is very important step. As we discuss here, right? Specification is not a simple term. When it goes to industry, it's very important term. The company will take what is the requirement from their clients. For example, there is a company called as Qualcomm. They will take the requirement from the mobile phone companies. What is your requirement? What you expect the chip should contain? The chip should have transmitter, receiver, audio video decoder, right? So Bluetooth module, Bluetooth controlling module, right? PCI peripheral controlling modules. So all those things, the specification team first they should decide the functional blocks required in an IC. Functional blocks required. What are the functional blocks required in an IC? Right? That they should decide. They should decide what is operating voltage, expected operating voltage. This IC is going to operate what voltage? What are the ranges of voltage? Which block? See, in an IC, every block need not to work with the same voltage. Some blocks may work with what? Different voltages. What voltage I should view for which block or which design? Right? So they have to decide that what is operating voltage. Frequency of operation. Communication strategies. Communicating protocols. From one block to another block, what type of communication they are doing. We have many protocols for that. Communication protocols. And next is power and estimated power consumption. So all these things you have to decide, and they should be having some discussion on this estimated power. So this after discussing this, now there is an architecture team. The architecture team decides which functional blocks should be given to whom. There are some functional blocks for which we cannot write the very large code. If my design, my IC wants amplifier or analog to digital converters, whether amplifiers and analog to digital converters can be implemented by using Verilog code? No, because those are analog circuits. I can write Verilog code only for digital circuits. Please write down that if you don't know. Right? Verilog or VHDL code, hardware description language works only for digital design, not for analog design. So they have to divide this entire designs, which is for analog, which is for digital. So second thing, after specification you have RTL design. So in RTL design, we use Verilog or VHDL only for digital designs, not for analog designs. Analog designs is done in different way again. If any analog circuits want, but most of the designs can be implemented by using what digital design. So that we use what RTL design. So in RTL design we use Verilog or VHDL, Verilog or VHDL to implement a design, to describe design. Why do you think Verilog or VHDL is used? Why can't directly we can write the circuits our design? Directly I can write the circuits, right? We have some schematic editors. Why we have to describe to some programming languages or any languages? Why we have to use that? See, if I have a mux, right, I can directly write what is mux. It has having one AND gate. This is connected to inverter. Here I have what one more AND gate, and for this you give what one OR gate. Okay, better here writing here. I'll write here. Okay, so here you have See, for example, you take a mux. Take a mux. So you know how to implement mux, right? But how to implement mux? You have what? And yet, here you have inverter. Here you have directly connected to AND gate, and here this is your okay. If you use inverter here instead of here, so here you use what? OR gate. This I not select line. What is this? I1. What is this? Output Y. So for this inverter, this one inverter. Uh, what is this inverter? Is so this is a mux. What is symbol for mux? This is a symbol for mux. I not I1. This line and this Y. So why do you think that? Why can't we write this directly? We can write this program, right? Why we are describing program languages? See, any specific programming language is easy. So its behavior is easy, right? If I ask mux, what is its behavior? Very simple behavior. You have select line, you have output pin. If select line is 0, what is output? Select line is what is output? Even if this whether this behavior is easy or writing structure is easy. Behavior is easy. Where you will ask the truth table for this reason only. Describing the circuit behavior is very easy. You take D flip flop. You take D flip flop. If I ask you to write the internal structure of D flip flop, gate level structure, how many will you write? You already done the digital design. How many will you write? Internal D flip flop structure. But if I ask you to write the D flip flop, you have D flip flop, you have Q, you have pin, right? Now, if I ask you people to express behavior, whether you'll do? Yes, you will easily do it. What is that? You have. If you can't do it, then you should revise it. That is your problem. It's not. If reset is 0, irrespective value of clock, right? If clock is 1 or not, we are not bothered. Irrespective value of clock, my output will become what? Q will become. If reset is 1, active reset. Irrespective value of clock, my output will become what? 0. When reset is not 1, if reset is 0, what happens? My Q is going to take what? D only at the positive edges. It is positive edge triggered flip flop. At the positive edge, my Q is going to take what? D. Simple behavior. So describing any circuits through its behavior is easy, but structure is difficult. I am just explaining a smaller design. When you think about bigger design, so easily we can describe through programs. Right? I can easily write a program for this mux Verilog program. What I'll write if s equals
So
0, what y will take? Y is going to take what? Else y is going to take what? I1. Very simple. Write through programming language. I can easily describe the behavior. So for that reason, right, we started using programming language to describe the design, which facilitate us to describe any circuits through its behavior, not through its internal structure. The Verilog or VHDL designer, if he remembers the behavior of a circuit, that is sufficient. By using that behavior, he can implement any circuit or any design by writing what Verilog or VHDL code. So here, design is in what form? Design is in what form? Behavioral form. Design is in the behavioral form. So bigger circuit, what they will do? Any idea you have? If you have bigger circuits, how they will code? They will use finite state machines. Right? They will use what? Finite state machines, FSM. So bigger circuits, what they will do is they will divide into different states. You have, for example, you take a ATM machine, you have different states. This is ideal state or reset state. Then this is what pin entering state or card entering state. Yeah, ideal state, yeah, entering state, pin entering state. Next is what amount entering state. How much amount you want? Amount entering state. Next, amount dispatching state. If you want to use IC for this, then you will split the entire bigger operation into small states. That is the behavior of your FSM, right? That is the behavior of your ATM machine, right? Right. When it's an ideal state, if you insert card means it is logic one. If you insert card, you go to what? Next state. If card is not inserted, it will be what state? Same state. That is logic zero. Now in pin entering state, if you enter the pin, you will go to what? Next state. Pin is
ఏమనుకుంటున్నానంటే ఏం చెప్తాను నేను అంటే ఇప్పుడు చేయాలనుకుంటున్నాను లేదనుకుంటున్నాను
right. From pin entering state, it will go to what? If you have logic one, means pin entering is validated. What state has to do? The state has to verify whether this pin, whatever entered, is correct or not through its database. If it is correct, then you will go to what? Amount entering state. If it is not correct, what you will do? You will throw an error, then you will go back to what state? Ideal state. Then amount entering state. If amount entered is validated means you have to check whether you have sufficient amount or not. Whether that amount you can dispatch or not. If I tell that give me 314 rupees 50 paisa, whether ATM can give, no. So whether you are entered proper amount or not. If everything is validated, you will go to what? Next state. Or else you'll go back to what? Ideal. See, you have to define here what this amount entering state has to do. But write the Gorilla program for that. Whatever amount is entered, right? Whether the amount is the sufficient balance is there or not. Just I'm giving you the overall idea because you cannot see if I give the FSM for I2C protocol, you don't know what is I2C protocol. Just I'm giving the bigger picture, like common example I'm giving. Right. What is the role of amount entering state? It has to validate the amount, like whether you have sufficient balance, whether the amount can be dispatched or not. You write the Varila program for that only. If you can validate the amount, or if you validate the amount, you have to put the output what? Logic one. You cannot validate the amount. You should output what? Logic zero. Based on this logic one or logic one, again you write the program. It has to go to which state? If logic zero is outputted, it has to go to which state? Ideal state, or it has to go to which state? Amount dispatching state. So amount dispatching state, what it has to do? It has to count the amount. It has to dispatch it. How much amount you want? If it dispatched, and after dispatching, it will go to what state? Ideal state, not at dispatched. Still not at dispatch. It should be remaining in what state? Amount dispatching state only. Till discounting and dispatching. So this is called as FSM. So bigger design, break into different and write the Verilog program to implement each and every state. What its role is there. So this is how the bigger design is coded into a circuit. So even this is described through its behavior only, right? FSM is what? Behavior of each state, what it is doing. So for that reason, so I can tell that RTL is in what form? It is mainly in behavioral form. Whether this behavioral form Foundry can understand? No. Foundry wants ultimately layout form. So next step is synthesis. But before synthesis, what are the steps we get is? I will tell you in brief. There are many steps involved before synthesis. One third step is functional verification. Like next step involves linting, linting. These are the main two steps after RTL design. What is functional verification? You have done the RTL program. You have to verify that RTL program is implementing the internet or not, or internet functionality or not. How do you verify? For example, you have written the program for Mux. How do you verify that? Or you have written the program for this ATM machine. How do you verify that? Apply different inputs and check it. Okay, in pin entering set, if I enter wrong pin, whether it is going for ideal set or amount entering set, check it, right? So, or you just consider this small example, Mux. Apply different inputs. Apply for I not, I1 and select line. You apply different inputs like 0, 0, 0. You apply. What's the output you're getting? I0 is 0, I1 is 0, select line is 0. What is the output you should get? Y should take what? Y should take I0 because S is what? 0. So apply different inputs and verify what is the output you're getting. Whether you're getting the intended output, then your program is functionally correct, or else your program is functionally wrong and revisit the program. That is called as what? Functional verification. So functional verification, the simple definition is verify functionality of a design. Verify functionality of a design by applying test cases. What is test cases? Or test vectors. Test cases or test vectors means the inputs what I'm applying to test it. So this process is not so simple. So you have to the test vectors in such a way that in the bigger designs, if you take a bigger designs, all these states are all the states are what? All the states are examined. All the states are verified. You should select the input vectors in such a way whether all the states are examined. Whether that is called coverage. Whether all the lines in the Verilab code is executed or not. All the lines. After the test vectors, whether all the lines are executed, all the lines are tested. That is called as code coverage. So there are some protocols like code coverage, functional coverage, right? So to do functional verification, you should learn UVM and you should learn like system Verilog. Also are very important. You should know how it is implemented, what test case I can implement. So mainly should be knowing UVM and Web system Verilog. What is UVM? Yes, good. Right. Universal. See, many will be knowing the concept, but they would have been forgotten the definitions, or they would have forgotten the full form. What is the at least you don't to understand what is functional verification in depth. Just at least you should be knowing what is a role they will do, because you are part of the flow. When you work in industry, right, you are part of the flow. If anything goes wrong, you should be knowing from where it is going wrong, which team have to communicate back. No one will tell you put the mail to this team. You should tell that I am getting some problem here. Please communicate to this team and release me the new netlist or something, new RTL.
The front end team will handle that UVM.
Yes, I'm telling front end, but you should be knowing you are physical design in the back end. You should be knowing whom it is. What is a team called as? Functional verification team or some team, it's called a design verification team. So they will be looking into UVM. So what is full form of UVM? Universal. Even we want some files from them also. UVM and means functional verification team. Even we want files from them. We want some file called save files, FTP files, VCD files. The files are not there. We have to discuss with them and we have to get those files. So universal verification methodology. So linting, what is linting team will do? See, functional verification is done. You understood that whatever RTL you have written, that is doing the functionally correct thing, whatever you intended to. Then you pass that RTL code, this RTL code for linting. What is linting will do? See, whatever the commands or whatever the programming language what you use in RTL, all the commands or all the constructs are not synthesizable. If you get the proper synthesis results, there are some protocols or there are some procedures or there are some rules you have to follow. If you're not following that rules, you will not get proper synthesis results. So linting will see that whether your RTL is ready for synthesis or verifies rules. It verify. It will not do syntax check. Linting will not do syntax check, but it will do some. It will do some verification on the RTL. There are some rules just be followed. It verify the rules in RTL and results after synthesis. It also came across like that. So I can. So what I did is I directly told them go to linting and get it corrected. Then only you get the good result in synthesis. Right. So linting is going to check your RTL whether everything is proper or not. If everything is proper, then only it can go for what? Synthesis. See, linting, they have many methods to check whether latch forming is happening, whether there are any multi-driven ports, whether hierarchy is correct, whether clock domain crossing is happening, whether synchronizers are added, any asynchronous circuits, asynchronous signals are there. So they have many rules. That rules they will take care and they'll add the synchronizers wherever they want, and they'll modify some Verilog constructs and give that they will give that results to synthesis. So after linting, the design is in what form? Behavioral form. This behavioral form my foundry cannot understand. My foundry can understand the layout of the cells. Cells means layout of the gates. Right? First I want gates. Next I can convert that to layout. Now who is going to convert to the gate? Synthesis team. Right? Convert this behavioral description, which is in the Verilog or VHDL, that you convert into gate level netlist. For that reason, we use synthesis. So what is synthesis? Converting gate level description into converting RTL netlist into RTL into gate level netlist. Then who is going to give you this gate level information? You have RTL behavioral description. You have to convert into gate level netlist. You have to do that. But while converting process from where you get the cells, ultimately you have to form the connection of gates, right? From the RTL, you have to form what connection of gates. Then what cell you have to use? So who will give this information? What is my question? I want to form the gate level connection or gate level. I'll tell you what is netlist later. Right? Then what gates I can use? Whether I can use AND gate, I can use OR gate, whether I can use MUX, whether I can use D flip flop. Who is going to give that information? So there is a team called as library generation team or library characterization team. From there, that team. So first I'll talk about library characterization team. That team receives the spice models from the foundry. Right? They receive what? Spice models from foundry. So what is a spice model? Spice models are nothing but the mathematical model of silicon. You have mod PMOS or you have NMOS. So how this NMOS and PMOS behaves in silicon, right? That same silicon I should how to use in the software. So how the PMOS is going to behave in silicon, how NMOS is going to behave in silicon, that we mathematically model it by using mathematical equations. We will model it by using current equations, by using threshold equation, by using temperature equation. So we mathematically model how this PMOS is working. That is called as what spice models for PMOS and NMOS. So they will get the spice models for PMOS and NMOS. By using the spice models, they will draw the schematic different circuits, different basic gates. Schematic means what? I think few colleges have this tools. I don't know, cadence tool or mental graphics tools. Yes, edit, edit. Cadence has worked so I don't know how many colleges have this. Right? You have to draw the schematic. They will draw the schematic of your and which gate is this? Which gate is this? And gate. Right? They'll draw this. What is this? Spice models. They'll get the spice models from what? Foundry. The spice models will differ for different technologies. The spice models, what are the spice models we have? That is different for 14 nanometer, that is different for 28 nanometer. Then what do you mean by technology? What do you mean by technology? If I tell 14 nanometer, what is the meaning of that? Channel length. Distance between source and drain is called as what? Channel length. For different technologies, we get different spice models. And by taking spice models, like I have a spice model for PMOS, I have a spice model for NMOS. By taking spice models, they are going to draw what? Schematic. And for this schematic, they'll apply different inputs, like different transition, different logic 1 and logic 0. This logic 1 and logic 0 doesn't have immediate change. They'll take some transition time, right? This. They'll take some transition time to follow. They'll apply different transition. They'll apply different load capacitance. From this, they'll calculate cell delay. Right? They'll calculate cell delay and power. What is the power consumption? Cell delay and what? Power consumption. And this information they'll pass to the layout team. This information they'll pass to what? Layout team. Layout team will draw the layout for this. Right? And for this NAND gate, they will draw what? Layout. Right? This layout they will give in the form called as LEF file. Layout of each and every cell they will give in the form of called as what? LEF file. And the cell delay and power information they will give in the file called as .lif. .lif file is called as a liberty file. LEF file is called as layout exchange format. So we are not going to draw the layout for cells. What cells we are using to for synthesis, right? For synthesis, layout is not required. It's required for physical design. For synthesis, this .lib is required. And who is going to do that? We are not going to do that. There is a separate library characterization team. So they will do all these things. They'll take the spice model, they'll draw the schematic, they will characterize the cell for different delays and powers, and they'll give in a file called as what? .lib file. And the layout team will take the layout, they'll take the schematic. For the schematic, they'll do what? They'll draw the layout and they'll give in the form of called as what? LEF file. So this team is called as full custom design team. This team is called as what? Full custom design team. In full custom design team only you have library characterization team, you have standard cell layout team, analog layout team. There are different teams again. A separate domain again. But we are not working on full custom. We are working on what? Semi-custom, means ASIC design. Now I went to this topic because who is going to give us the .lib? There's a library characterization team, or there are separate vendors for that, separate companies. They work only on generating this .lib files by taking the schematics from the by taking the spice models. They will generate a .lib. In .lib, I have information of standard cells. Right? I have why they are called as standard cells. So first I'll tell you what are standard cells. So now it depends upon this .lib generator or the person who is generating the .lib. What cells you want to include in the files, right? So generally they include cells called as NAND gate. Means they will draw the NAND gate schematic and they'll calculate what cell delay and power. Right? NAND gate, NOR gate, XOR gate, OR gate, AND gate, uh, inverter, buffer, mux, D flip flop, half adder, full adder, right? Some DFM cells are designed for manufacturability cells. Right? So all these cells, your library characterization team will draw the schematic and they'll give you what? Cell delay and power consumption. In which file? .lib file. In .lib file, I have standard cell information. All these are called as standard cells.
Physical information of the standard cell is also present there. In not
No, it is not present. It is present in left. Physical information means layout information. This .lib has function. Timing means cell delay. Power, it has power, different types of power, and it has functionality. Functionality means what is the functionality of that cell. So functionality of AND gate is what? Y is equal to A and B. This functionality equation is present in .lib. That is how my synthesis tool is going to understand what it's doing. Right? Now, why these cells are called as standard cells? They are called standard cells because when they draw the layout, right? When they draw the layout, all the cells are same height. Almost all the cells are having what? Same height. Height of a standard cells are same. What is this height? Height of a layout. This height is called as what? Height of a layout. All the cells have same height. Width may vary. This is width. Width.
Hello,
I
sir.
am not talking W by L.
Hello, sir.
I'm talking about
Hello,
layout
sir.
height and layout. All the cells will have same height. Yes,
Hello.
yes, please tell me.
Hello, sir.
Yes, please tell me whether it's not audible.
Sir, I do not understand inverse gate letter buff marks d flip flop half adder full adder. I don't anything. But can you describe again buff?
So you don't know what is the half adder? That is what you're telling.
Uh, yes, sir.
You don't know what is half adder.
Sir, can I draw the circuit?
No, what is your question? You tell me.
Sir, my question also, can you describe the buff?
Buffer is nothing but buffer. Buffer is nothing but a circuit which is going to pass the same signal. It is a short form of buffer. If you have A here, the same
like
A you will
like
get here.
like sir, like D flip flop.
No, it's not D flip flop. Flip flop is different. Flip flop is going to pass a signal only at the clock signal. But buffer is not like
Only
that.
the clock signal.
Buffer is a cell which is going to pass the same signal. So buffer is back-to-back connected inverters. I can tell like that. In a cell, I have back-to-back connected inverter. That is called as buffer.
Back to back inverter.
Yes.
Okay, sir. Thank you, sir.
How buffer is implemented? Buffer is nothing but back-to-back connected inverters. Why buffer? That will understand in physical design. Then what is the role of buffer? See, instead of buffer, I can have on same net, right? Here also A, this side also what? A. I can have metal layer. Instead of why I should use buffer signal? Hmm?
delay.
To generate delay, that is one reason. To fix the hold violation, intentionally we should add the delay. One reason. Second reason is buffer has different role in physical design. That will understand later why the buffer. See, if I start talking about buffer, right? See, for example, you have bigger net length. Net length is very big. If you want to break the net length, what you will do? You have to insert one cell. If you insert any other cell, the logic will change. Here, the input you will get different. Here, output you will get different. Right? Instead of that, to break this net, what we'll do? We use a buffer in between. So we used to break the nets. This net, what is buffer will do is it will improve the signal. See what happens if I have bigger net is the transition of a signal is degraded, because the transition of signal means the A will take more time to charge, A will take less time, more time to what? Discharge. Actually, if the digital logic is there, what would be the digital logic? It should show this behavior, right? Immediate charging, immediate discharging. But if I have long net, it will take more time to charge, more time to discharge. That will lead to many other problems. Short circuit power, timing violations. Antenna violation will not. Antenna violation is because of charge. If they don't have any path for discharging, that is called antenna violation. But this is different. Short circuit power it may lead to. I have already done for one batch, I think. I've taken the PD basics. I've done for one batch. So this transition, if you want to reduce, then you want to reduce its net length. How to reduce the net length? To reduce the net length, right? You use one buffer here. If net length reduces, net capacitance reduces. If net capacitance reduces, the transition time also reduces. So to break the bigger net, we use buffers. Any of this concept we'll do in advanced topics. You need not to worry about that. Now just understand, focus on the topic like what are standard cells. Standard cells are the cell which is having what? Same height. These are the cells. See, DFM means design for manufacturability cells. Even these cells you will understand in physical design, like you have tap cells, end cap cells, D cap cells, filler cells. There are few cells like spare cells or tie cells. Right? So all those cells are present in standard cell library. Now, what are inputs for synthesis then? Inputs for synthesis. Yes, I'm talking about this input because it's a previous step of physical design. Right? What are inputs for synthesis? So one is a dot V, no doubt about that, because that RTL is very important. RTL. What is next thing?
Dot liquid.
Dot V or dot VHDL, right? Anything, both. Dot V is very log format. Dot VHD is HDL format. Dot lib, right? Dot lib is having what? What dot lib has? Yes, a timing power area and functional information of standard cells. Functional information of standard cells. So my synthesis tool is going to convert this RTL to the gate level at least by picking the cells in what? Dot lib. Right. Next is what? Dot. Let me see.
Hi, pardon me. Like, I have one question.
Please tell me.
Hello? Yeah,
Yes, please
see,
tell
for
me.
example, if there are some complex circuits, the complex circuit contains of standard cells and remaining cells also, right? For example, LED, some other analog circuits. So this RTL consists of both the standard cells and the other cells also. If like
Yes,
dot
macros
lib
can be
consists.
instantiated.
Okay.
Macros can be instantiated. RTL has macros instantiated. Like in your RTL, you want PLL, right?
Hmm.
For example, you have two blocks. One block you've already implemented. You have another block. The frequency is different. This block clock frequency is different, and this block you want PLL. So PLL can be instantiated in RTL. That is not synthesized because if for example you have PLL in RTL, you are already instantiated PLL in RTL. Then directly you should use dot lib for PLL. There's separate PLL dot lib.
So, but you are telling dot lib consists of only standard cells.
See that we are telling for basic
So
understanding
in
purposes. Here we have
okay,
students even
okay,
directly coming from the UG classes, right? So we are
okay.
telling from
So
basic for
okay,
a smaller designs. When you talk about the macros are already instantiated in the RTL. They should take care, right? It's already instantiated in the RTL.
okay.
So when it's already instantiated, so for that any macro or any analog macro or any other macro memory macro, there should be some information, right, for the synthesis tool to do. So then for PLL or macros, I should be having dot lib again.
Okay. So in RTL, everything will be included. In dot lib, only standard cells will be included.
See, dot lib, you can have plenty of dot lib. You need not to have only one dot lib. See, if your RTL has
Yeah, yeah.
macros, right, here you should
Hmm.
have standard cell dot lib. Along with that, you should be having dot lib of PLL, dot lib of memory macros. Any macros you're using, you should be having dot lib for macros also.
Okay.
Without dot lib, again, my tool cannot understand that. What is the delay, then what is the
Hmm.
power consumption.
Okay. Got it. Thank you.
Like our netlist is also have two types, flat or hierarchical.
Hmm.
So how we can check that?
You will be having different submodules, right? In one module, you will be having top module. Top module will be calling different submodules. That you'll understand. When you go to the first topic is first we'll show the netlist, which is hierarchical netlist. In that you have a main module. In main module is calling different submodules, right? No, flat doesn't have any submodule. For example, you take one design, right? Full ladder. You take parallel, you take full ladder. Directly you can write what full ladder you can directly implement, like what is full ladder? You have two XOR gate, right? You use two XOR gate, right? A, B, and output of this XOR gate, sorry. Output of this XOR gate again you're giving to what? One another XOR gate. Just I'll give one example. This you are giving to what? See, this is going to generate what? Sum. This is flat. But the same full ladder I can implement by using what? Two half adders. So this full ladder is one main module. This full ladder is having two sub modules. What is that? Full ladder is having two sub. For example, you assume that this half adder is not present in my dot lib. Directly the cell is not available. Directly half adder is not available in my dot lib. Then what I will do? Full adder I will implement by using what? Two half adders. So I have two sub modules here, and each half adder is having internal cells. Its own what flat design.
So by opening the when we have to see the content of the file.
See, if you have only one module, it is a flat design. If you are having different modules, so one module is calling another sub-module, and for this half header again there is a again there is a program, then that is called as what? Hierarchical design. Right? Hierarchical design has one module calling another module. Yes. Why it is called as hierarchy? Because one module is calling another module. Another module can call what? Another sub-module. You have principal. Any information has to be passed to the student. He will not come and go and talk to all the students directly. He will first intimate all HODs. Principal is calling different sub-modules. HODs, they'll not directly go to the classes again. They'll call the class teachers. Class teachers will communicate to the students. That is called as hierarchy, right? In similar way, program, the design can be different hierarchical things. Why the different hierarchical things? Why they cannot write the program flat? Why we have different hierarchy? The principal can go and do the class in all the classes. No, same way. Entire SOC will be divided into different blocks, different teams. Okay, this you handle. A you handle this. B team you handle this. C you handle this. D you handle this. E you handle this. So A team again, if they have any small blocks, they will give to separate engineers. They will write only that small Verila programs. All these Verila programs are integrated. For that reason, many hierarchical design is going to form. Right? Because one person is not going to write the design for entire chip. Different persons is going to write the different RTL, and everything is integrated. That is called RTL integration. That's if I not mentioned, because I'm not going to discuss front end in depth. But in reality, there is RTL integration team. They'll take all the small RTL and they're going to integrate into bigger RTL. For that reason, we have different hierarchies available in the design. So you have a RISC core processor. What is RISC core processor wants? You want a CPU. One person will write the Verila program for that. You want what? PCI module, peripheral control interface module. Another person will write the program for that. You want SDRAM module. SDRAM means memory controller module. SDRAM module. Another person is going to write the program for that. You want clocking module, means which different clocking, different clocks should reach different modules, right? You want clocking module. Separate, another person is going to write the program for that. All these programs, your RTL integration top team will take, and they will integrate all the different RTL. Now, your RISC core modules has how many submodules? CPU submodule, PCI submodule, and STRAM submodule, and iClocking submodule. Like this is called as hierarchical design. Hierarchical design generally it forms because one person is not going to code all the things. If he is doing right, if one team is doing, the time to market will be very huge. The entire design will be split into different things, and they will reuse the design, right? They will not write the PCI controller, they will not write the program every time. If already Verilog code is present, they will reuse it. So RTL can be in a hierarchical form. Netlist can be in hierarchical form. It cannot be in hierarchical form. It depends upon synthesis engineer. You can make netlist flat. You can remove all the hierarchy. Means module boundaries you can remove it. You can make netlist. That is, you have plenty of options in the synthesis tool. You can make that. So next you have STC. So what STC is consists of? See, I will mute the audience. If you have any problem, right, you can unmute and you can answer. To avoid this unnecessary noise, right? That's it. So HTC has a timing constraints. Timing constraint you understand later. What is that? Mainly in timing constraint you have what? Clock information. So information. What clock your design is using, how many clocks your design is using, what is the frequency of a clock, right? So next is clock uncertainty, like that, right? You have different clock uncertainty, what is clock transition. Next you have set input delay, set output delay. So all those things you have in HTC file, that will understand later why each and every command is used. Now I can tell only in simple way, like whatever design we are synthesizing, right, from RTL to netlist, it should work with particular clock frequency. I should synthesize in such a way that my tool is going to work with this clock frequency. If my design is not working with this clock frequency, then it's of no use of synthesizing. I should synthesize in such a way that, or I have to improve the design in such a way that my design is meeting this requirement in simple terms. But HTC has a different commands also that we'll discuss later. I cannot discuss now because it is separate topic again. STA, static timing analysis. We'll discuss that. See, doing synthesis without HTC is very easy, but with HTC is it's not difficult, it's challenging. Right? You have to meet this timing requirement. You have to meet this clock frequency. Right? For example, your parents tell that go to VLSI Guru and come back, whatever mode you want. What you will do? Book a cab, come here, go back. Easy. But your parents tell that go with 20 rupees and come back. It's challenging, right? Get a bus, get a BMTC bus, right? Come in bus, get down with VLSI Guru, again go to the bus, use a map from where you have to board, everything you have to plan it. The same way. Without constraints, synthesizing is easy. With constraints, where the engineers have to put a lot of efforts to meet the timing. So these are three main things for logical synthesis. There's one more thing called as physical synthesis. That I'm not going to discuss now in the demo class. That we'll discuss in the advanced part. But it's the main thing for logical synthesis. These main files we want. Some other files like for power, if you want to accurate power, then you can use save files. All those things are there. But to synthesis happen, these three files are sufficient. So if everything synthesis is good, then what is output of synthesis? Output of synthesis, gate level netlist. What is difference between gate level netlist and RTL then? Gate level netlist is also .v or .vhd. It is .v or .vhd. Then what is the difference?
All the information.
See, .v or .vhd can have any constructs of Verilog or VHD available. But gate level netlist should have only gate and its connection. Both are .v files. And RTL is for any technology. I can use for RTL any technology. If you tell that use RTL for 14 nanometer, I can use. If I tell the RTL use for 180 nanometer, I can use. RTL is not written for any technology, but gate level netlist is for particular technology because gate level netlist is having the cells present in what? .lib. And .lib is characterized for what? Particular technology. Because I told you how .lib is formed. Spice models we obtain for particular technology. So I can tell that gate level netlist is for particular technology. The same gate level netlist for 14 I cannot use for 28. But the same RTL I can use it. These are two differences. One is RTL can use any constructs. RTL can use if statements. RTL can use assign statements. RTL can use always block. But gate level netlist cannot use all these things. Gate level netlist should have only gate and its connection. You understand what is gate and its connection? You know how the RTL is? No, I don't know. Okay, I'll give you an example. You have a or get and get inverter. So this is like in 1, in 2, right, in 3, this is out, right. This OR gate is having A1 pin, A2 pin, Y pin. This AND gate is having A1 pin, A2 pin, Y pin. This inverter is having A pin and Y pin. Now how to write the RTL for this, sorry, gate level netlist for this? So you have what? Module name, like module name I'll use it as temp. Next, inputs. What are the inputs? In 1, in 2, in 3, outputs Y. Right? After that, this is intermediate nets. Intermediate nets are nothing but called as what? Intermediate signals are called as nets. So this is net N1. This I'll call as what? Net N2. So I have to declare that first. Wire N1, comma N2. If any net is coming out of a flip-flop, any net is coming out of a flip-flop, then it should be declared as a reg. It cannot be declared as wire. It can be declared as what? Reg. That is part of Verilog. Right? You need not to worry about that. Now, I have a cell. So what happens in your netlist is you have only cell and its connection. Only this information should be present in the netlist. Cell and its connection means first you have this cell name is present in the library. Library means what? Dot lib. Dot lib, for example, this OR gate is having a cell name called as R2. R2 means a 2 input OR gate. Now, next my synthesis tool will give one instance name. Instance name is U1. What's the instance name? U1. Why is instance name? Because in my design, I can have n number of OR gate. From one OR gate to another OR gate, I should be having some small difference. That difference we identify through what? Instance name. Next, dot A1. Dot A1 means where this A1 pin of your OR gate is connecting to. A1 pin is connecting to what pin? What port? In one port. Dot A2. A2 pin is connecting to which port? Into port. And comma output pin. Dot Y is connecting to which net? N1 net. So this is called as gate and its connection. Each pin of your gate is connecting to what port or what net you are going to define it. This is over. Dot Y is connecting to N1 net. Next cell. What is your next cell? AND gate. What is next cell? 2 input AND gate. This is the name of a cell, how it is present in .lib. Right. So what is the instance name? My tool will give, synthesis tool will give different instance name. So this instance name is not same for any two cells. It's always different for different cells. So dot A1, A1 is connected to which net? N1 net. A2 is connected for which net? In 3 net. And Y of this pin is connected to which net? Into net. Next, last, what is that next thing? Inverter. This is a name present in .lib. So next instance name is U3. Dot A is connected to which net? N2 net. Dot Y connected to which net? Out. So end module. You have end module.
Module- See, in module tab, output should be out now.
What you told?
So in first module temp, you have assigned an input pin and then output. So output should be out instead of Y. Output
Okay,
should
okay.
be
See
out.
this. I have not written. No, I think in Verilog we use input and output only. It's not in and out. Whether we are using in and out.
He's saying,
Well,
oh, you have mentioned the output as OUT, right? But here you mentioned as
okay, okay,
while.
okay. Yes, yes, yes.
Yes,
Correct.
yes,
This mistake I have done. Right? What I have done is output. What output of this entire design is what? Out.
out.
Yes. Okay. Fine. Now, what is this RTL is having? This sorry, Netlist is having only gate information and its connection. What is the connection? Where the connection is maintained? See, N1 is output of what? Y, right? This N1 is what? Output of Y pin. You can see N1 is output of what? N1 is connecting to Y pin of your OR gate, and the same N1 is connecting to what? A1 pin of your AND gate. So then the connection is maintained. Right? N1 is connecting to Y pin of your OR gate, and the same N1 is connecting to A pin of your AND gate. So the connection is maintained. Similarly, here also, right? N2 is connecting to Y pin of your AND gate, and the same N2 is connecting to A pin of your inverter. The connection is maintained. So only this information should be present in the net list. Any other statements is not allowed. Like assign statements, if statements, anything you have in the net list is not allowed. Only should be having gate and its connection. That is the first difference between your RTL and gate level netlist. So your gate level netlist should have only gate and its connections like this. Second difference, RTL is independent of technology, but gate level netlist what depends on technology. It's not. I cannot use the same gate level netlist for different technologies. Yes, that is the role of synthesis. See, I'm not going to go into synthesis in depth. All these things we'll see. Synthesis will do one or two classes even in advanced level also by using tool. Right? We'll give the tool and we'll do it. So after synthesis, the design in the gate level form, where the design is present in the gate level netlist. So in the here we have gate and its connection. What type of gate I have to use? That my synthesis tool will depend to meet what? Clock frequency information. Right? And to meet the functionality. After synthesis, we take care different things. One is we use uh, we can do LEC logic equivalence check or formality check. So we do logic equivalence check. Logic equivalence check. What is logic equivalence check will do? Whether your gate level netlist and the RTL, you have to Verilog, right? Whether both are implementing same functionality or not. All right, it checks gate level netlist and RTL, verifies gate level netlist and RTL. RTL for functionality, whether both are implementing same functionality or not. See now I have they will do like gate level simulation, but there is some small difference happens after, right? So here they can do gate level simulation also. See here RTL is not having any cell delay, but after gate level we have what? Cell delay. Right? In gate level I have also have what? Cell delay. So I can include the cell delay and I can might uh, gate level simulation team, they can do gate level simulation also. Right? Gate level simulation. Gate level simulation is nothing but what? Gate level simulation is the same simulation what we discussed here. Functional verification. They will do again here. Same. But here, what is the difference? We have in the net gate level netlist, we have what? cell delay. So while doing the RTL simulation, so just they will verify whether the output is getting some proper logic or not because of what different inputs. But here we have to verify whether my output is reaching here within predefined time or not. Because here I have what even net delay and gate delay. Right? This gate delay and net delay. So here they will do gate level simulation. This includes even cell delay. It includes cell delay and net delay. All these are areas where you will find the jobs in real estate. There is a separate team for LEC check, separate team for gate level simulation, separate team for synthesis, separate team for linting, separate team for function verification. Right? It includes cell delay and net delay during simulation. During the simulation, at that time there can be some differences, and again they have to go back. They have to modify RTL. They have to change their synthesis, and if there is any problem, they have to verify that why there is a problem. Then there is our next team called as DFT team. DFT stands for what? Design for testability. What this team will do? Design for testability. No, they not a test. Why they will do? See, once a chip is fabricated, right, you will give the GDS. Your GDS is fine. You understand that your GDS is fine. You are sure about that. But after fabrication, foundry cannot ensure that chip is working properly because the fabrication happens in nanoscale. First of all, fabrication happens in what? Nanoscale. Nanoscale means what? 10 to the power of minus 9. Whatever scale you have, you are seeing 10 to the power of minus 3. That is in millimeter scale. The smallest unit is what? Millimeter. You divide by 1 lakh times, then you will get what? 10 to the power of minus 9. How small it is, even you cannot see through your eyes. Okay. So they had to use microscopes, everything. So even when you ensure that your GDS is good, but foundry cannot ensure that the chip is fabricated properly, all the chips, right? Because each chip may have their own defective parts. See, while manufacturing, so there are two reasons for that. One is the design is the fabrication happens in nanoscale, and entire fabrication is chemically driven. It's not mechanically driven. It's not like you have a metal layer and you cut the metal layer by using what? A grinder, right? And cut it. Not like that. You remove this. If you want to form the metal layer in this region, you cannot form it. First of all, you cannot form the metal layer in this region because it is in the nanoscale. First, you have to form the metal layer for entire this region, and only if you want metal layer here, right? You cover by using a mask and cover by using oxide layer. Remaining regions you etch by treating this entire metal layer, entire metal with acid. This region is not exposed to acid because we have already covered through what? Oxide layer. Other regions are exposed to what? Strong acid. So only this region will be retained. Other regions are etched. That is called as etching. So only I have metal layer in this region because of the treatment of acid is not good. Right? So the metal layer will be fabricated like this. Metal layer is not planar. I'm talking in nanoscale. Right? Metal layer is not planar. It is like this. Another metal layer, it can be etched like this. So without our knowledge, there is a short here. Because the spacing is also in the nanoscale. Without our knowledge, what is happening here? There is a short. So this type of problems may be seen in IC, which even foundry can't identify the problems, some problems in IC. right? So once chip gets fabricated, once chip is fabricated, you have to test it. How do you test it? Without testing, if you send to the market, right? If you send, for example, you have a SoC for mobile phone, you will send to the mobile phone designer, and if the chip is having some functionality problem, then entire company will lose its market. Again, the mobile phone manufacturer will not purchase the chip from the silicon manufacturing companies or silicon design companies. So they have to throw the defective chips and they have to only retain the functional chips. So how to decide that which chip is working properly, which chip is not working properly, which chip has some defective elements inside? How to test it? Test by applying some test vectors. See, if you have a
By
Ethernet
giving
controller chip, you will not connect antenna and you cannot check that. You will not do that. What you will do is you apply some test cases, test pattern, and you check that what output you are getting, and from that output you validate whether your design is working properly or not. So to facilitate this checking, verifying the chip after fabrication is called as post silicon validation. Verifying chip after fabrication is called as what? Post silicon validation. To facilitate this post silicon validation, this DFT team will add some additional cells in the design. They'll add some additional cells in the design without disturbing the functionality. That is what the role of DFT team. Role of DFT team is to facilitate the chip can be tested easily, right? So that is the role of DFT team. So DFT team has different uh, I can tell different logics for that, like scan chain insertion, automatic test pattern generation, built-in self-test. There are many things for that. So what is DFT? Add some in basic terms. If I tell, add some additional logic in design. Add some additional logic. Logic means cells. Right? Additional logic in design. In design now, design is in what form now? Gate level netlist. Adding logic in design means add some additional cells in the gate level netlist. They have to decide how I should add. That is the role of DFT team. Add some additional logic in design so that chip can be tested easily after fabrication. So that chip can be tested. Be tested after fabrication. It is the role of DFT team. So after DFT, I'll get to some modified netlist. I'll get the netlist only, but in that there is some additional cells. Like my flip flops will be replaced by scan chain flip flops. So you'll understand that what is scan chain flip flops, everything later. So some modification happens in netlist by DFT team. After that, that netlist will come to which team? Physical design team. So next is our role starts. Next, the physical design role starts. Physical design. The physical design team has a major responsibility. The physical design team has major challenges, and even their package is also very high. Right? Not at immediate stage, later stages. The physical design happens like, see, why it is having a major concern means, for example, you will be having the 3 months to do physical design. So you have started doing physical design of your design. You have 3 months to complete. When this gate level simulation will be happening, they will not ask you to wait till that point. They will add DFT and gate level simulation. They will be doing their role parallelly. So when they are doing this, DFT will be doing their role parallelly. So when the DFT complete their role, immediately the design will be sent to what? Physical design. You will start doing physical design. Then you are done 2 months. 2 months of physical design you did that. And you have only last 1 month to left out. You're not completed. You are in the process of doing physical design. You have only last 1 month left out. Then your gate level simulation team tells that there is some problem with simulation. I'll change the RTL. So there is no extension of project deadline. Within 1 month, again you have to do the everything from the beginning. That pressure you have to handle during the tape out time. Means that is what expected from PD engineers. Everything tool will do. Physical design is totally tool will do. You have to handle this pressure. You have to handle this process. Right? How efficient you handle. See, if you get this netlist modified at the last stage, you tell that I'll start from the beginning. You do it. You work day and night. It's up to you. Or you use some additional TCL programming methods or some methods. If you use and if you the change the cell, if you directly include in your current design, if you have capability, you do it. That's up to you. How do you handle it? Ultimately, you are the responsible because you are the last step of ASIC design flow. The project deadline will not extend for physical design engineers. They have all the steps. Even RTL, they have all the time. Even in the last day, also they will change the RTL. Like some small cells, they will change. Like 4 to 5 cells, they will change in the last stage. Then we have to handle it. Right? So we have more responsibility in closing the design. It's not that this phase is this after completing all this stage, we'll go to physical design. Even in the process of gate level simulation, also we'll start with what physical design. We'll start running the trial run. They may change RTL at any time. Again, you have to handle that. You have to do it again and again. Right? So physical design, as name only tells, the gate level netlist has a connection of gates. You have to convert into connection of layout. Right? So physical design converting gate level design into physical level or layout level design with what by meeting see, doing without constraint is easy. We have to meet area requirement by meeting area requirement. Next, by meeting timing we have to meet. Third thing, we have to meet what? Design for manufacturability, design rules. I can tell design rules and design for manufacturability. Design for manufacturability. The area requirement, you have many parameters to judge. So timing means it is like STA. Design rules means DRC. Right. So design for manufacturability means a DFM. So after DFT, your physical design starts. See, after DFT again they may go for synthesis also. They may go for synthesis. They can come back. That is the iteration process. So now physical design. See, first I like the steps in physical design. Right. That each and every steps we are going to cover in our thing. So I will write what and all we are covering it. See, any student who is very new to this, because for other students we have already done it. Physical design flow in the basic physical design classes. So whatever we cover in our course, I will write those topics, what we cover. See, we will do physical design of physical design. The physical design first starts with partition. Physical design first starts with what? Partition. So what is partition? Partition. Yes, see, you have a bigger chip level. So doing physical design of full chip is very difficult because full chip has 3 lakhs to 4 lakh cells, even 30 lakhs to 40 lakh cells. See, physical design max to max we can do for 1.5 lakh cells because the runtime is there, right? Runtime is there. So tool to handle this many cells. So what we do is bigger design. We split into smaller designs. So this bigger design is called as a full chip level design. This is full chip. And smaller designs are called as what? Blocks. These are called as blocks. So the bigger design is split into number of blocks. So there is a chip top, right? Generally, chip top team will be there. The chip top team handles this. They will split the entire design into different blocks, and each block is given to each engineer to do the physical design. So engineers are responsible for doing the physical design of each and every blocks at the initial stage. When you become experienced, then you handle the full chip level design. Even companies may outsource the blocks to do the physical design. I have a Qualcomm, and I am the manager of Qualcomm. Just I'm using the name only for example purpose. I'm the manager of Qualcomm. I have a big chip has to be designed. I have divided into different blocks. And to implement these blocks, I may not use the engineers of same Qualcomm. I will use the engineers of service-based companies. There are different service-based companies. Different service-based companies engineers come to Qualcomm and they'll implement their blocks. And I'll take all those blocks as a manager. I'll coordinate with all the block owners, and I'll integrate it. Our entire project, whatever entire project you have, right? This entire project will go to a product-based company. Will give entire project to service-based companies. Service-based company, they will be having a team lead. He will handle this entire full chip level design, and the block level design will be given to the other engineers. So basically, the freshers and till the experience of 3 to 4 years, you will be handling different block level design. Right? So this block, see, there can be even a full chip level design, smaller full chip. If I have a chip and this chip has only 1 lakh cells, then I'll not split it into different blocks. So only each person will handle this entire full chip. That is also possible. So now you understood what is block level physical design and full chip level physical design. Full chip level physical design includes what? Integration of all the blocks. So generally here we are doing partition splits full chip into different blocks. Splits a full chip into different blocks. It is area splitting and as well as what? Module splitting. It is like you have a area, you split exactly half, like that, right? Your Verilab netlist has to split into what? A module should be splitted. It's not a area splitting. One block owner may get many cells, another block owner may get what? Only less amount of. That is also possible. Because it is not a area splitting, it is a module splitting, netlist splitting. It's not a area splitting. Area is not divided like two halves. They will not split the area. If I split into two halves, one half of the Verilab code will go for one person, another half of the Verilab code will go for another person. They cannot implement physical design. Give different submodules. Right? So different submodules handled by different components. It's module splitting. basically partitioning means. So now we will do the in our design we'll do block level physical design. Block level. See, even we'll discuss the full chip level design as theory part, but as a lab part we'll do what? Block level physical design. How to do this block level physical design. This is theory lab. So block level physical design we do. See, in this block level physical design, right? What we will do? What we will do? So we'll start with floor planning first. First, we start with input files. Input files for PD. What are the input files? We first discuss about input files. Complete input files. So I am not going to discuss about input files. I'm just writing what we anyhow we are going to do that. What are input files? Entire input files for PD. Next is we will do floor planning. And that is what input design is nothing but input files only will cover. After input file understanding what we'll do, we'll import to the design only, right? Floor planning. So floor planning is nothing but so floor planning has different steps. What are different steps in floor planning? Creating core and die area. Die area. What is core and die area? For this, now I'm discussing only about block. I'm not discussing about full chip. For block A, you assume, right? For block A, I have to create what? Core and area. So how to create this core area? It's not general how I draw, right? Generally, you create on block. It's not like that. It's the area estimation. This block A has how many cells? What's the area of cells? Means layout of cells, layout area of cells. So based on that estimation, I have to create what? This core area. This is called as core area. This is called as core area. This is called as what? Die area. This core area, die area. So creating core area and die area is not straightforward. We have to estimate how to create core area and die area. Sometimes we will not create core area and die area. Sometimes chip top only will give what? Core area and die area for my design. He'll give the coordinates or he'll give these coordinates. What is your coordinates? This coordinate, this coordinate, this coordinate, this coordinate. Or he'll give the def file, design exchange format file. So we'll discuss that, how to create core area and die area. What are different methods to create core area and die area. Next is a port placement. Next is port placement. So we will discuss on port placement. So port placement, what is what are ports? Ports are input and outputs of your block. So inputs will come to your block through ports. Output will go through your block from your block through what? Ports. So if I have this ports, what your full chip level designer will do, he will connect only to what? He will connect only to what? Ports. So he will connect only from B to B, B port of B to what? B port of B, and like this, he'll make the connections. Only he'll connect the ports. So what is your role? Connect this port to what? Internal design. Input ports you connect to internal design. From the design you connect to what? Output ports. So this you will do in the last step, but you have to place the ports. First only you will place the ports. Why? Port placement is not in your hand. It is in the hand of what? Full chip level designer. If at all your block A is communicating to block B. If you have block A and you have block B, both are communicating. Outputs of block A is going to block B. Then where you will place your output ports of block A? You will place here. Whether it will be good if you place here. You should place on what side? Right side. Then only you can make what? Easy integration. So block A is getting inputs from block C. Then you have to place input port at the bottom side. Like based on the chip top requirement, you have to do what? Port placement. That is called as port punching. So later you understand that how to do the port placement. All the different methods. How can you do the port placement? Next is you will understand macro placement. See, in our design we have 40 macros. So you understand macro placement. What is this macros then?
Analog blocks.
See, you want to do cooking. Cooking you are doing. It's memory blocks PLL, right? You want to do cooking. In this cooking, you want to do different items like anna, sambar, something and all you have to do. You want to do some puliogre, you assume that. Whether you will start cooking from the beginning, like the puliogre powder, you will start doing it. Directly you will purchase from the shop, right? Puliogre powder. Directly you mix with water, your rice. Puliogre powder is done. Your efforts is reduced. Directly you are purchasing puliogre powder from the shop because you are not sure that you are going to get that taste when you prepare. Second thing is it is going to reduce your efforts. The same thing, few designs which are already optimized. It can be optimized in our company or it can be optimized in some other company. Optimized means what? The design is improved or that is the best design. That will directly purchase and we'll use in our for two purposes. One is it's going to reduce our efforts. I have to write the Verilog program for its macros. I have to do synthesis, and for that synthesis, I have to do physical design. Instead of doing that, directly I will purchase the layout of macro and I'll implement. I'll use in my design. How is that? Right? You have two half adders. You are doing physical design of two half adders. Directly, you have layout of one half adder, layout of another half adder. Connect it both. It is done. This one half adder is what? Macro. Another half adder is what? Macro. You are not writing any Verilog program. You are not doing anything. Directly, you are purchasing this layout from the vendor, and directly you are connecting. It is done. Your role is done. Physical design is simple. But you are not purchasing this half adder. You are writing the Verilog program. You are doing synthesis. You are getting basic gates. That basic gates, what you are doing? You are. How many basic gates you get? You will get 5 to 10 basic gates. That basic gates you will do physical design. Which one is better in this? First case is better, right? Directly purchase the two half adders and directly connect it. So few designs which you feel that you can directly utilize the layouts, and those designs are best designs. Then directly you can purchase and directly can use in your designs. It did not have to be only macros. Anything you want, if you feel that you can directly use it, you use it. So you have one block. You already have one processor. It's already designed. And next time you want to implement some other thing, additional thing. Additional thing, you write Verilog code and you implement it. But this processor is already there, right? You already implemented. Last time the chip is already there. The chip is already tested. This processor chip is already tested. This chip is already tested. And this new design for this processor, I want to add some additional facilities. Only for this additional facility, you write a Verilog program, you do synthesis, and you obtain the netlist. This processor, whatever you have earlier, directly use in design. Directly make the connection. Right? Then what is this design? The design is what? This design is a macro. You're not writing Verilog code for that. Directly using in your design. So this macro can be a previous designs, or you can purchase from some other person. You feel that it is more efficient. It is more efficient design. It's silicon tested. This macro is already working fine in the silicon, right? Then you will directly purchase it. That is called as what? Macro. So what is macro? Macros are complex designs. Generally, you purchase complex designs only, right? Because complex designs will give you more cells. Doing physical design for more cells is very difficult. Directly purchase that complex design. Macros are complex, which are optimized. Which are optimized. Sometimes they are silicon textured also, right? Which are optimized. Then only you purchase, or else you will not purchase this macro, or you will not use this macro. If this pullover powder is good, then only you purchase, right? Or else why you will purchase? You will not purchase.
Sorry, like this one will be in the gate level netlist already, right? The art.
Need not to be. You can directly use the. Okay, this macro is
Hello.
instantiated in gate level netlist. Only you have instantiation of a macro.
Yeah. Okay.
You understand what is instantiation, right?
Yes.
Other
Yes.
students
Like
will
what
understand what is
I'm.
instantiation later. We'll show the netlist. There only you can understand what is instantiation. But as per the question asked, macros should be instantiated in the netlist. But inside macro, you have cells, right? That need not to be present. Only macro terminals should be instantiated. Macro and its terminals.
Hmm.
Got it?
Yeah, like this macro in the gate level RTL also will have this macro gate level netlist, right?
See, RTL can use RTL. They can use it, or they can use in the term of. See, before synthesis, this macro will be present.
Okay.
It will be present in the RTL.
Okay. So whatever we are
Yes,
receiving
if
netlist, there is
your audio is
already.
disconnecting in between. Yes, this whatever cells we use, including macros, that should be present in the netlist.
Oh, yeah. Okay. Just
See,
for
I will give you an example. Like
mm,
see, later, I'll do an example also. Like when we go to advanced class, right? We will do an example to understand what is macros also, and hierarchical design also. This macro should be present in the netlist, and macro should be instantiated in the netlist. It should be instantiated in the RTL also. But what is inside macro? We are not using it directly. We are using the layout inside the macro. But why it is present in the netlist? We should be knowing where it is connecting, right? This macro is connecting where? For this, I have Verilog code. For example, I have Verilog code, and at last I use macro name. For example, this macro name is uh, processor. Right? I directly use processor. This macro name, and what are the pins? For which pin is connecting? For which pin, which cell is connecting? For this pin of processor, which pin is connecting? That should be present in what? Netlist. The macro connection should be present in the netlist.
okay.
Yes, this is what your
Yeah,
question.
it will be. Yeah, no, it will be there in the gate level netlist, and this name macro, it will be there exactly the same in the RTL netlist also, like, or we are
Yes.
checking
See,
the
macros
where, and
should
we
be
are
used in RTL netlist.
analyzing the macro.
Macros should be present in RTL also. Macros should be used in
Okay.
RTL also. They should
Okay,
insert
they
it in
will be
RTL
also
also.
using the macro which is optimized.
Yes.
Okay.
There can be even analog macros. Analog macros, I
Yeah.
cannot use what? Verilog program. I can directly use analog macros. Even that should be instantiated in the RTL. See, for this macros, right? Again, macros are different kinds. Soft macro, hard macro, right? Discuss later. But for macros, compulsory we should get what? For macros, I should be having dot lib. I should be having layout. What is that? Dot left. If I want to use this macro in the physical design, then I should be having what? Dot lib, dot left. I have to purchase this from the vendor. Dot left has layout information and dot lib has what? power and timing information of macro. Now, macro placement is very challenging in physical design. That you have to understand. In this entire area, where I have to place macros.
Okay.
So where you have to place macros, we have to decide that. See, macro count will be less. Like we will not use, for example, we have 50,000 cells. We will not use all the 50,000 cells as macros. Macro count will be like less than 100. So for that reason, first we will do the macro placement. Like we will give the place where my macro has to be placed. You will decide that. Like these are the macros which I've already placed, complex cells which are directly used. Right. So what are the guidelines for macro placement? How to place macros? If you do macro placement wrongly, what is the effects you are going to see? All these things we are going to discuss in macro placement. So in our design, we use SRAM as macros. SRAM, memory macros. We don't have PLL, we have SRAM. Yes, macros are the design which we are going to reuse again, or it is instantiated in our design. See, macros should be instantiated in our design, but what is present in the macro, that is not required. Inside a macro, we have directly what? LEF. But macro, this macro name and where this macro is connecting, that should be present in the netlist. That is called an instantiated. What is macro? What is where it is connecting? Right? For which port it is connecting or which pin it's connecting? That should be present in the netlist. That is called as instantiation. That instantiation should be present in the netlist. Then only my tool can understand, right, where this macro is connecting, or else I cannot understand. The netlist will not only have the standard cells, it also has macro information. But what is inside macro, netlist is not having. Where it is present? In the LEF. LEF has what? Layout information. Ultimately, we want only layout. That layout is already present in LEF. So there are few companies, only they work in generating macros. Right? They'll sell their macros. So you are very good. You write the program for ARM controller. Do contest. Improve your IC and sell it to some designer. Mobile phone, you have ARM. In mobile phone SoC, you have ARM with what other blocks also. If your ARM processor is very good, they can purchase it. They can purchase it. So macros can be implemented by any person. Even this block level physical design is also a kind of macro. For what? For whom? For full chip level designer. For full chip level designer, even block level design is also kind of what? Macro only. What he is doing, he is not worrying what is present inside your design. Full chip level designer. He will be only implementing what? Integration of blocks. That is what you are also doing here, right? You're not worrying what is present inside the macro. You're worried only connecting the macros and the standard cells. For full chip level designer, your cells, your block will act like a macro. So after macro, next you have power planning. Next we describe one power planning. See, power is very important. We have to decide the power. All the cells, 50,000 cells. You know what is CMOS. You have PMOS and NMOS. This PMOS requires VDD at this end, and NMOS requires VSS at the other end. This VDD and VSS, this is an inverter, right? This VDD and VSS is required for every cell. All the 50,000 cells should get what? VDD and VSS connections. If your design has 50,000 cells, macros and cells should get the power connection, and there should be no IR drop. IR drop happens in the design. Why? You
Due to
have a
charging of
voltage here. You have voltage here, 1.5 volts. This is your VDD. At lower technology, VDD itself is 1.5 volts. It's not 5 volts or 2.5 volts. VDD itself is 1.5 volts, 0.75 volts. When you go to lower technology, the VDD will also scale down. VDD itself is 1.5 volts or 0.75 volts. So you have 1.5 volts. You have a metal layer, and this metal layer is connecting to your standard cell. Like you assume inverter. This inverter will draw the current for function to charge the load capacitance. What it will do? It will draw the current. At what conditions this will draw the current? This inverter. I think after studying CMOS, this should not be a bigger question. No, what are the situations it will draw the current? It will draw the leakage current, right? Leakage current is there. What is leakage current? Even when MOSFET is off, some current will be flowing. From where this current will flow? From the battery only, right? One is leakage current. Next one is what? Short circuit current. What is short circuit current? When PMOS and NMOS both are on, direct current flows between what? VDD and ground. That is called a short circuit current. Third one is switching current, charging and discharging the load capacitance. At these 3 times, your cell will draw the current from what? Battery. When it's drawing the current, right? This metal layer has a resistance, correct? Small resistance. This metal layer is having what? Small resistance. It's the internal feature of metal layer. The current is flowing through this metal layer. So you have V is equal to IR. Ohm's law. Through this metal layer, current is flowing, and this metal layer has what? Resistance. Out of 1.5 volts, some 0.3 volts will drop here. So how many volts will reach to your cell? 1.2 volts. You have 1.5 volts VDD, but how much is reaching to your cell? 1.2 volts. This is called as IR drop. IR is nothing but called as what? Voltage drop. Voltage is dropping near to your cell. If voltage is dropping near to your cell, it affects its performance. Performance means your cell delay will increase because of that. If voltage drops, current will drop, right? Because current is nothing but what? ID is equal to what? VGS minus VTH the whole square. Mu and C naught of X W by L VGS minus VTH the whole square depends upon VGS. VGS means what? VDD only. If VDD is dropping down, your current will drop down. If current drop down, cell delay increases. So to avoid this IR drop, I should see this net length is reduced or net resistance. This resistance is reduced. So for that, I should do the proper power planning. So how to do this power planning? How to reduce IR drop issues? So all those things we'll discuss in what stage? Power planning stage. After power planning, we'll get the issues like some of the power is not reaching to the cells. Some of the power is not reaching to the macros. How to fix those issues? There is a real-time issues. Doing power planning is easy, but fixing the issue is difficult. All those issues we have to fix it. There is a recent interview questions. How did you do the power planning and what are the issues you have fixed? So once you prove that the power planning is done, see here there is one step I have missed, like add some tap cells and handicap cells. Right here at D, add tap and handicap cells. We'll discuss. Next, we'll discuss about what? Power planning. Why tap cells? You know what is latch problem?
Yes,
Discussed in
sir.
CMOS.
By
So
reducing
to avoid that latch problem, we use what? Tap cells.
capsules.
How tap cells solves the problem? Why we use handicap cells or boundary cells? So all those things we'll discuss during this stage. So next is placement, right? Next step is what? Next step is placement. What is placement? Generally, will not directly go to placement. This is a flow, but in the course, what we do is after power planning, we start doing STA, static timing analysis. We'll do what? Static timing analysis in the course. Because when you understand STA, then you can understand placement, or else you can understand placement. In STA, we will discuss about, I'll just mention the topics like different types of cloth, different types of cloths. And again, cell delay, net delay. What is latency, skew, jitter. Next, we'll discuss setup and hold analysis. Setup and hold, including latency, skew, and jitter. Next, we'll discuss something called as a false path, and multi-cycle path. Next, we'll discuss on recovery and removal checks. Recovery and removal checks. Clock gating check. Next is we'll discuss on timing fixing methods. Timing fixing methods. That setup and hold, how to fix it. Right. So DRVs, design rule violations like max cap and max transition violation, max trans and max cap violation. How to fix it. All those things we'll discuss. These are the main points I covered. There are a lot of things to discuss again, like PVT conditions, how process voltage and temperature is going to affect your cell delay, PVT conditions, MCMM, multi-corner, multi-mode. All these things we discuss in STA. And we also discuss some low power technologies. Low power technologies. The low power technologies is discussed there and there, wherever it is required. So low power technology, what we are going to discuss here is clock gating cell, power gating, clock gating cell, power gating, multi voltage design, and different threshold voltage design, different VT cells. How to implement this? What are the cells required to implement this? Right? Low power technologies. See, in your design, you have a camera module. You are going to turn on the camera only once in a month. Then why I should give the power to all those cells, right? Camera module says why I should give the power. If I give the power, my battery will get what? Drained. Cut the power when the block is not used. That is called as what? Power gating. Cut the power when the block is not used. When any block is not used inside IC, cut the power. Cut the VDD. If VDD is cut, what happens? There is no leakage power. If leakage power is not there, unnecessary my battery will not drain. That is called as power gating. Clock gating means You have D flip-flop, right? Your D input is not changing. D input is 0 for 5 seconds, but your clock is continuously changing. This clock is changing, right? That is going to switch the internal gates. Instead of D flip-flop, you have what? Internal gates. So because of switching internal gates, there is a dynamic power. So cut the clock, you cut the clock when the input not changing. When input changes to 1, then only you give the clock. At the positive edge, your 1 to what? 1 will be passed to what? Q. So give the clock when the input is changing. When input is not changing, cut the clock. That is called as what? Clock gating. Stop the clock. Multi-voltage designer. Different blocks operate at different voltages. You have different blocks in the design, operate at different voltage. See, when any block, if I operate with higher voltage, right? High voltage, I have less cell delay, but I have more power dissipation. I have a processor. This processor requires fast operation, then operate at higher voltage. But I have peripheral control interface with PCI module. This doesn't need a fast operation. Then don't operate with higher voltage, operate with lesser voltage. So this here you use VDD 1.5, here you use VDD 0.95. What happens if I use VDD 0.95 here? The dynamic power dissipation will get reduced. The power will directly depend on what? VDD. So here power will reduce, here I'll meet what? Frequency of operation. So like that use a different voltage for different blocks. That is called as multi-voltage design. Different VT cells that I'll discuss later. Different threshold voltage cells, HVT cells, RVT cells, LVT cells. So these are the different things which we discuss apart from the normal flow, how to implement. Next, we'll discuss on placement. What is placement? Placing all the standard cells inside the core area. Plenty of standard cells we have, right? Place inside the core area. So how to do the efficient placement? So during placement, I have to meet the timing. How to meet it? I have to meet the area. How to meet it? I have to see that while placement, right? I have to see that whether all the cells are routable. Means all the cells can connect. I can connect all the cells in such a way that you place all the cells. So when two cells are having connection, one cell you don't place at this corner, other cell if you place at this corner, what happens? You have to route like this, right? Instead of that, place two cells what nearby. Easy connection. So place the cells in such a way that easily routable. So we will study all the issues of placement. Placement stage. If placement stage is good, next stages will be good. So next is what we study about CTS. Factory. No, we will not place here. Port placement is already done, right? It's already done. Where you have to place? What do you mean by IO pins? It's already done, right? Port placement is already done. That step I already mentioned here. Ports are input and outputs of a block. Pins are input and output of a cell, standard cell. When cell is placed, inside that pin is also present. Pins are input and outputs of a cell. Ports are input and outputs of a block. So block port placement you already done. Pin, there is nothing called as pin placement. When cells are placed, pins are also placed because pins are present inside the cell only, right? See, tool, you don't worry about that. Tool uses the same name for different port placement. Also, it uses the same command. Like IO pads, also it uses some same commands. Port placement, I have place pins only, but generally it does port placement. The command is pins only, but it will do the port placement. You don't worry about that. But ports are nothing but input and outputs of a block. The pins means input and outputs of a cell. But command, if you have place ports, we don't have any command. We have place pins. Pins means in the command point of view, it is ports only. There is nothing to place the pin separately. That is, pins are present inside the cells directly. So tool will use same names for pins and even as ports. It will use the same term called as pins only. So next is what? CTS, clock tree synthesis. So here you have to understand why we have to build clock tree. What are the parameters governing clock tree? How to build efficient clock tree? This clock tree should not violate this setup and hold. That is called as what? Building efficient clock tree. So how to build that? That we'll discuss in CTS stage. Next, routing. Next we'll discuss routing. Routing is nothing but what? Connection between cells. Right? Connect each and every cell by using what? Metal layers. Connect the cells by using what? Metal layers. That is called as what? Routing. After routing, you have to do the checks. LVS and DRC. Sanity checks are done at the beginning only. Right? After routing, do DRC and LVS check. What is DRC? Design rule check. Means while doing routing from one metal layer to another metal layer, you have to maintain minimum spacing. Right? Like that, there are many rules how to maintain in the design. What are those rules? Whether I'm maintaining that rules or not. That check is done on the design. LVS means in the gate level netlist, you have the connection between cells. Whether the same connection is maintained in the layout or not. Verifying that is called as what? LVS. Layout versus schematic. Layout, this is a layout. Here you don't have schematic. Your netlist only is schematic. The connections present in the netlist, the same connections are present in the layout or not. In the netlist, cell A and B is connecting. But in the layout, also cell A and B should connect. Same connections are maintained or not. That is called as LVS. So after that, we'll go for sign-off checks. Sign-off checks. Sign-off checks means the final checks. So in sign-off checks, we do checks called as power and IR drop check. Power IR drop check. So we'll also do electron migration check. Power IR drop, EM check, electron migration check. Next, second we do what? Timing check. Next we do physical verification. The power IR drop and EM check is done by a tool called as a radar tool. In Fusion compiler, we can directly use inside, but you need this license, radar tool. You need a license called a radar tool license. For physical design, we use ICC2. We use what? ICC2. For this check, we need what? Radar tool. For timing, we want prime time. Separate tool it is. Prime time. For physical verification, see, physical verification checks DRC on metal layers and also on the base layers. Base layers means polysilicon, diffusion, right? N-well, P substrate. Those are called as what? Base layers. Metal layers means it is used to connect one cell to another cell. It will check, it will do the DRC on both the layers, base layers and metal layers. It will do LVS, it will do ERC, electrical rule check. Right? This physical verification, we use IC validator. So industry also uses IC validator. Industry also uses caliper. Caliper. So these are the different checks called as sign off checks. So then, so no, see, we are not going to use this redact. We don't have license for redact. Other two things we can do, but we are not going to do this. We don't have redact license. And that is a separate team, it's not a part of PD. All these three are separate team in industry also. They are not part of physical design, but physical design should be engineers should be having knowledge what they are doing. That will cover in theory. But industry they are separate team. IR drop team is separate, timing team is separate, physical verification team is separate. But the theory part will cover what they will do, what are the checks done. If issues comes, what we have to do, that will cover. So these are the things what we do in physical design. So here, right, from here to here. So in the routing stage, we have layouts get connected, and in the sign off stage, we verify the timing, power, and the rules what you get from foundry, they are maintaining or not. Right? So physical design in Virasai Guru happens in two modes, weekend and weekdays. You know this already, right? Weekend and weekdays. Weekend, you have theory, everyone should attend. Weekend is for what? Theory, where everyone should attend. Weekend means Saturday and Sunday. Weekdays means Friday to Thursday. One day it will be off. Right? Weekend theory, everyone should attend, and even we have weekend lab also. Weekend labs. And during weekdays, we have weekdays lab. This theory is common for everyone. This weekend labs, those who cannot attend weekdays lab, they can attend what? Weekend lab. Both labs are different. There is no continuation. Weekend lab is different and weekdays lab is different. Students who can attend weekdays from Monday to Thursday, they can attend what? Weekdays lab. There will be some working professionals who cannot attend the weekdays lab. They can attend what? Weekend labs. Right. So weekdays lab will be from Monday to Thursday for 3 hours. Weekend there will be theory, and for weekday students there is no lab. And for weekend students there is both theory and lab at the weekends. Right. So this is how the thing works. So from the tomorrow, I think from tomorrow we'll start the theory class. Tomorrow is Sunday, right? We'll start the theory class. So the lab admin will inform you when it is going to start. Weekend lab probably will not start from tomorrow, it will start from next week. Weekdays lab will start from next week. The admin will inform you from when it is going to start, what is the timings. Coming to placements, very important question. The placements are very simple. You first learn what is taught. Only these questions are asked for freshers. If you are a fresher, if you are an experienced candidate, right? See, I'll come to that. If you are an experienced candidate, right, then you should learn some other different things apart from the. I mean, sir, this is okay, but one or two things like lower technology nodes, and if you want to apply for any experience, like what is the experience you have to apply, what design you have to explain, right? That knowledge you have to be using. So first complete the course, right? Then clear the mock interview. We'll conduct a mock interview. Regularly we'll conduct, not only at the end. So clear that mock interview. After mock interview, you will be added to the placement support. If you have any requirement, we'll put in the placement support too. So once you get into the industry, right? Industry as a fresher, industry will pay you 15,000, not more than that. 10 to 15,000, because till you get the client. Once you get the client, your salary will be 50,000, 40,000. It depends upon the company. What is there? It will be nearly above 40,000. See, I've already mentioned the tools here. ICC2. We are using ICC2. It is synopsis. It's not cadence. So why is 15,000, right, at the beginning? The companies, some companies will internally they will also use their training tools. The tool itself is very costly. The tool ICC2 what we are using, right? That license is like 8 lakhs per year for 20 license. Tool itself is very costly. They'll use a tool, they'll train you. See, once you complete one tape out means one this design cycle in a company, right? Your range will change totally. Because company is not sure that you are going to complete this tape out or not. Because you should use your knowledge, you should use handle the pressure, you should complete the tape out. If you complete one tape out, then you will get enough experience. Then your salary is not like a hike, a small hike. Your salary will double. Your package is 4 lakh, it will suddenly jump to 8 lakhs or 10 lakhs in the second year. But first year it will be little bit struggle, because unless and until you complete one tape out, company will ask you to complete one tape out means from starting to beginning you have to do one cycle, one design you have to do. From second design, right? They will surely give you the second, because first design more than you doing, you require help, because every company they have separate flow. Synopsis has, see, if the person who's experienced in Synopsis, if he's going to Intel, he need help because he's having a separate flow there. You need a help there. So when you are exposed to that help, means that project, then second time you will do by your own. So your salary package will change. Second year, third year, you have to tell. You will only tell it what is the package. Fourth year and fifth year, it is totally different. So you will earn like more than 1.5 lakh from the fourth year. Okay? So that is about the placements. So now see, last year we saw a total dip in placement, physical design. But this year is very good. Now already students are already placed. It is not with VLSI Guru, entire placement was very down for physical design for last year. But now it is very good. Right? Now the placement is very good. Students are not going. They message me, sir, I'm not going to this company because they have more bond. They company will take a bond of 2 years or 3 years, right? When they recruit you. So the students are rejecting the offers. That is the situation what is happening now. Okay, this is about placements, right? When I have also told you when your salary will increase, what happens to your salary when you grow. And layoff, coming to layoff, right? It's very less in the case of semiconductor industry. But till now, I have not seen the layoff, but we saw last year. Last year we saw because there was a huge dip in the. I think we also seen some layoff in semiconductor industry also, but not what we saw in as like what we saw in the software. It's very less because training you to the level of 3 years, right? The company has to put a lot of its effort. So not too easily, but only if they don't have and they are paying you 1.5 lakh, then they'll do the layoff. But after that, they yes, multi-voltage design includes UPS. Right? We cover the low power aspect of all the four. Power gating and multi-voltage design UPF will teach the UPF. Unique power format. Power domain levels will be teaching that. See, you will have to do Can give one
श्वास भी लेगा